This is over the periodic table and the development of the atomic model. The first thing I'm going to cover is the periodic table because it is vital to our understanding and our chemistry class this entire year. We've already talked about Lavoisier. He compiled a list of 23 elements. By 1870, 65 elements were known. 1935, 88 were known. And today we have about 117, and we're still growing. We talked about Lavoisier a lot. You are expected to know him. You're expected to know his contributions. Johann Dobryner, we're not going to really mention him much. We mention him at this point to give him some notoriety because he did arrange things in groups of three. He did try to come up with a periodic table. He used math and the chemical properties to group them. Other than that, we really won't mention him beyond this point. John Newlands, arranged by groups of 8 or octaves. We really just kind of mention him and note him and go on to the big players. Dmitri Mendeleev. He's the first to publish the most successful order of the periodic table. That's what makes him so important. He published in 1871. The one thing you need to know is this right here where we talk about increasing atomic mass. He arranges by increasing atomic mass. There's someone else later on that we're going to talk about that does it differently, and he has a reason for doing differently. And that's our current periodic table, the new one, which is based not on Dimitri's, but it was a good start. He also made predictions about elements and their properties based on trends they saw in the periodic table. We talked about that a lot. We talked about germanium and gallium. He revised the periodic table into 17 group table. Remember, he had these holes like 44, 68, 72, where he was able to describe their characteristics and physical properties based on the group around them. And later on, they did discover them. All right, these guys, Lord Rayleigh and William Ramsay, these guys are responsible for giving us our noble gases. Remember, the noble gases are a group which are noble. They do not interact with others. They are inert. They have a full octet or a full amount of valence electrons in the outside shell. We're going to learn all that in a little bit. It's really hard to separate all this because they all interchange and intermingle with one another. So these guys, Lord Rayleigh, we'll talk about him when we talk about light waves, and William Ramsay, they're credited with discovering the gas argon. It didn't fit into the groups that Dmitri has, so you know what you do? You make a new group. And they won a Nobel Prize in 1904. Okay, boom! This guy, Henry Moseley, he organized by atomic number based on X-ray crystallography. He's actually not American, he's actually English. He went through there and looked at Rutherford's experiment after Rutherford discovered the proton, and he subjected the elements to X-rays, and then he got a reading between the frequency and the spectra of the elements, and he said, you know what, I see a pattern here. And so what he did, he rearranged based on the atomic number. The atomic number is also the number of protons, and we're going to learn all of that. It's also just kind of interrelates to one another, so it's hard to separate. But this guy's important. You better know him. This is the guy who rearranges our periodic table by atomic number, and that is the periodic table we use today. Okay, these guys basically did the periodic law. The periodic law is a repetition of characteristics along a repetitive property that can be distinguished with a mathematical relationship. The mathematical relationship is important because it gives you standing with what you're doing. We always want to try to back up with math. And so this whole time we've been kind of bouncing around with the whole range of the periodic table was based on, bam, periodic law. Okay, Glenn Seaborg, he's awesome. He gets an element all to his own because of what he did. He placed the lanthanide and actinide series in the bottom of the table. Now, this group, it always changes depending on what periodic table you're looking at. Lanthanide and actinide on y'all's periodic table appears here. On other periodic tables, they appear here. They're bounced back and forth. Then nobody can agree on if they belong here, if they belong up here, and if 71 and 1 and 3 belong over here. But basically, he came up with this series, this group right here, because he saw a property emerging that loops them all together. And we'll see another property that loops them all together too. It's the last major change of the 20th century. If we really looked at the periodic table and put it into its full, beautiful arrangement, we would see that it looks like, bam, this. And that's really hard to fit on a piece of paper. That's why we actually moved this group down and shorten it up so it can fit onto a single sheet of paper. So that is the periodic table.